This lesson deals with biasing the BJT. You can find these notes in the ECE302 ebook in Chapter 3 starting on page 30. In our last video, we analyzed a BJT circuit. That particular circuit is called a fixed bias circuit. And what that means is if beta F varies, the operating point varies. And the only way to get a fixed operating point with that circuit is to have a fixed value of beta F. But beta F is very temperature sensitive, and it's also sensitive from part to part. In other words, if you buy a handful of the same transistors, you might find that beta F varies maybe between 100 and 300. We'll see later in the course that you get that best performance from an amplifier if the operating point is independent of beta F. The main problem with the fixed bias circuit is that if beta F increases, then I sub C increases. If we could design our circuits such that we decrease I sub B when I sub C increases, then we keep the operating point in a small neighborhood. Back on page 24, in our fixed biasing circuit example, when it was in the active region, we found that I sub B was VBB minus V sub B over R sub B, where V sub BB was the battery on the left-hand side of the circuit, and V sub B was the base voltage back to ground. If we could get I sub B to decrease when I sub C increases, one way to do that would be to try to increase the value of V sub B. We could do that by adding a resistor. We want to make V sub B increase when I sub C increases, because that's going to subtract from our battery, and that'll lower the base current. So by adding a resistor here, current is equal to I sub B, but that's roughly the same as I sub C in the active region. This node voltage is equal to 0.7 plus the drop across here. So as I sub C increases, this increases, and then I sub B decreases. That should hold the operating point more stable than it was before. Let's do an example and see if it actually works. Here I've added a 1K resistor to this circuit. I have a 1K here, a 10K, and two batteries. Let's find the operating point if beta F is 100, and if beta F were to change to 300, let's find the operating point again. Let's assume that VBE on is 0.7 and VCE set is 0.2. Whenever you see the word bias, that refers to an amplifier circuit. So I'm going to guess the active region, and then we'll check it to make sure it's in that region. But that'd be a good first guess. Between the base and the emitter, I'm going to put a battery of VBE on. Between the collector and the emitter, a current source of beta FIB, where beta F is 100. I have a collector resistor of 1K connected to a 20-volt battery back to ground. I have a base resistor of 10K and a battery of 9 volts, and then I've got my emitter resistor back to ground of 1K. Label everything we can on the drawing. Here's I sub B, here's 100 I sub B, so this current is 101 I sub B. So I need to solve for I sub B and VCE to show that I'm in the active region. If I go around this loop, I have an equation that has only I sub B in it. The rise in voltage is 9, the drop is 10K times I sub B, plus 0.7, plus 101 IB times 1K, and that's this equation right here. Let's solve for I sub B. So it's 9 minus 0.7 divided by 10K and divided by 101 times 1K, and that's 74.8 microamps. The collector current is 100 times that, or 7.48 milliamps. Let's solve for the collector emitter voltage. And one way we could do that is to think about the fact that this node voltage is 20 volts. And that's equal to the drop here, plus the drop across the collector emitter, plus the drop across the emitter resistor. If I take 20 volts and subtract this drop and subtract this drop, I'll get the collector emitter voltage. 20 volts minus 1K times I sub C, and then minus 1K times 101 I sub B. Plugging in I sub B and I sub C, I get 4.97 volts. I sub B is greater than or equal to 0, and VCE is greater than VCE sat of 0.2. So we are in the active region. If beta is now 300, we have the same circuit, except that we're just going to change the value of beta F. I just go around this loop, it'll give me one equation and just I sub B. But now the current in here is I sub B plus 300 I sub B, or 301 I sub B. 9 volts is equal to 10K times I sub B plus 0.7 plus 301 times I sub B times 1K. And that's this equation here. 9 minus 0.7 divided by 10K, but now divided by 301 times 1K. And that's 26.7 microamps. I sub C is 300 times that, so we get 8.01 milliamps. And the voltage here is 20 volts. Take 20 volts minus the drop across R sub C, and then minus the drop across the R sub E, we get the value of VCE. That's about 3.96 volts. What's happened here is that I sub B is decreased by about a factor of 3, and the value of I sub C stayed about the same, and the value of VCE stayed about the same. Let's do a little comparison with this example and the one on pages 22 to 24. So in our fixed bias circuit, when we had beta F of 100, we had I sub B of 77 microamps, I sub C of 7.7 milliamps, and the collector emitter was 7.3 volts, and we were in the active region. But when beta increased to 300, our base current stayed the same, our collector current increased to 14.8 milliamps, but now we were in saturation. With this example, when beta F was 100, we had 74.8 microamps for I sub B, 7.48 milliamps for I sub C, and 4.97 volts for VCE. When we tripled the value of beta F, that's a 200% increase, I sub B was 26.7 microamps, I sub C was 8.01 milliamps, and VCE was 3.96 volts. We had a 200% increase in beta F, but I sub C only increased by about 7.1%. I sub B readjusted itself to hold I sub C nearly constant when there was a huge change in beta F. Our last biasing example, we had two batteries to bias the transistor in the active region. Nobody wants to have two batteries in their circuit. Let's see if we can do this with just one battery. This is called an emitter biasing circuit with one supply. It's also called a self-bias circuit. So here I've got four resistors, one transistor, but now only one battery. I want to find the value of I sub B, I sub C, and VCE for different values of beta F. In fact, let's let beta F approach infinity and see what happens. Whenever I see a battery connected to 2 points, what I like to do is to draw the battery twice. That kind of breaks the circuit apart. Now the current that's coming out of this 15-volt power supply is equal to the sum of these two 15-volt power supplies. But they have the same node voltages, so therefore they're equivalent. But when I do that, what I've got here is a linear circuit that I could Thevenize and put it back in. And in fact, it'll look like our previous example. Let's find the Thevenin equivalent circuit. To recall from ECE302m, we take the load off and find the open circuit voltage. You just have a voltage divider because the current in these two resistors is the same. It's going to be 5K over 5K plus 10K times 15, and that's 5 volts. To find the Thevenin resistance, we set all the independent sources equal to 0, so we're going to short this and look back, and we see 10K in parallel with 5K, and that's 3.33K. Call that R sub B. Now this circuit looks like our fixed bias circuit with emitter feedback, but we're doing it with a single power supply. Let's analyze this circuit and see what happens. Let's assume that VB on is 0.7 and VCE sat is equal to 0.2, and given beta F is 100, let's put in our active region model between the base and the emitter, VB on at 0.7, between the collector and the emitter, a current-controlled current source of beta F IB. Here's I sub B, here's I sub C, which is 100 I sub B. This is 101 I sub B. We pretty much have the same analysis we had in our earlier example. If we go around this loop, we have an equation only in I sub B. 5 volts is equal to I sub B times 3.33K plus 0.7 plus 101 IB times 1K. We can then solve for I sub B. In this case, it's 41.2 microamps. I sub C is 100 times bigger, or 4.12 milliamps. This time, let me find the collector emitter voltage by taking the difference of two node voltages. This node voltage here is going to be equal to minus I sub C times 1K plus 15. And this node voltage is 101 I sub B times 1K. Plugging in I sub C and I sub B, I get 6.72 volts. The base current is greater than or equal to 0, and the collector emitter voltage is greater than or equal to VCE sat. So we are in the active region. Beta F increases to 300. All that changes here is just this term right here becomes 301. This is now 14.1 microamps. This turns out to be 4.24 milliamps. And now the difference of those two node voltages is 6.51 volts. Why is the collector current staying the same? Well, I sub C is beta F times I sub B, but I sub B has a term here, beta F plus 1. But this is huge when you multiply that by 1,000 compared to 3.33K. Multiplying I sub B times beta F, we have a term in front, basically, of beta F divided by beta F plus 1. So the collector current doesn't change much as long as beta F is large. What if we take this idea a little farther? Suppose that beta F begins to approach infinity. Now, this can't physically happen. 300 is about the upper limit for beta F. But if you could have a much higher value of beta F, what happens? I sub B is I sub C divided by beta F. If I sub C is finite, then dividing it by a huge number makes this get smaller and smaller. Now, when you do that, it makes the analysis a lot easier. In other words, if this is very, very small, then the voltage across here is equal to minus 0.7 minus a small number plus 5. So that makes this 4.3 volts. And that makes this 4.3 milliamps. And that makes this 4.3 milliamps. The voltage across the collector emitter is going to be 15 volts minus 4.3 minus 4.3. We're able to get the voltages very quickly without a lot of analysis and find that the voltage across the resistor R sub B is 4.3 volts, which gives us 4.3 milliamps for the currents, and the collector emitter being 6.4. You can see in these previous examples, that's what we're tending towards. We start out at 4.12 milliamps. Beta increases, we go to 4.24 milliamps and then 4.3. So this is sort of where it's heading, the bigger and bigger beta F is. This is a trick we use in IC design to chop away some of the equations. I won't use this a lot in this course, but there'll be a few examples where I use this technique to get roughly the neighborhood of the answer. Let's develop a design procedure for picking the resistors R1, R2, RC, and R sub E. If you want the current in the collector to be fairly constant with variations in beta F, which is roughly equal to the emitter current, I need to pick the resistors R1 and R2 such that this voltage here, V sub B, doesn't vary much with beta F. One way to do that is to pick the current in this resistor to be much, much greater than I sub B. So what's the largest value that could ever appear here? Well, we could calculate that and make that resistor current here 10 or 20 times bigger. If I do that, then this current is roughly the same as this current, and I just get a voltage divider of R2 over R1 plus R2 times V sub CC. How about the resistors RC and RE? Well, it's common practice to drop about a third of the power supply here, a third here, and a third here. If we do that, then the voltage at V sub B is roughly going to be equal to a third of the power supply plus VBE on. But if that's much, much bigger than this, then this voltage here is again fairly constant. Let's try our algorithm out on an example. Let's pick the resistors R1, R2, RC, and RE. If I sub C is 2 milliamps, using a 12-volt battery, a VB on of 0.7, and suppose that beta F varies between 100 and 300. We'll see later as we look at data sheets that every transistor has a value of beta F that varies with the collector current. And usually most manufacturers will recommend an optimal value of I sub C. Suppose it is 2 milliamps in this case. Well, our technique says we're going to drop a third of the power supply here. So that's going to be equal to 4 volts. The current in here is I sub C, so 4 volts divided by I sub C would give me 2K. The collector current and the emitter current are about the same. Put 4 volts across here, and my current is about the same, then I'll get also a 2K resistor. What's the largest value of base current we're ever going to see? The base current is equal to the collector current divided by beta F, but the smaller beta F is, the larger I sub B will be. So we'll take the smaller of the values here. 2 milliamps divided by 100 would be 20 microamps. If I pick the current in this resistor to say be 20 times bigger than this value, that would be 400 microamps. I could say that this current is roughly the same as this current because this is so much smaller. All right, what's the voltage V sub B? Well, it's going to be equal to 0.7 plus the 4 volts that I have. That'd be 4.7 volts. The resistor here is going to be 4.7 volts divided by the 400 microamps we're going to put in that resistor, and that's 11.75K. The voltage across the resistor R1 is the difference of the 12 volts with my value of V sub B, which was 4.7. And again, the current's about the same, at 18.25K. The nearest standard resistor is 18K, and for here, 12K. In this example, I picked a factor of 20, but why don't I pick a factor of 200? That would make our approximations even better. But the problem with that is if I make this current go up, then this resistance goes down, and likewise this one goes down. What happens is I draw more current in these resistors. My battery doesn't last as long. So this is a trade-off. We're doing this to get a fairly constant operating point, but if we overdo it, we'll kill our batteries. Let's analyze our design using, again, standard components. I didn't show the analysis here, but it's the same as pages 33 and 34. With the values that I have here. I get a collector current for a beta F of 100 as 1.96 milliamps and 2 milliamps for a beta F of 300. So we're in that range that we were shooting for. Our collector emitter voltage varies a little bit, although it's not real critical because it's the voltage across the current source, and our base current is changing a lot to compensate for the change in beta F. Let's take a look at biasing a PNP transistor using the resistors R1, R2, RC, and RE. Now in PNP transistors, we have the emitter pointing into the transistor, and normally in schematics people draw the current flowing from the top of the drawing to the bottom. You don't have to do that, but that's a common notation. I'll draw the emitter on the top and the collector on the bottom. Let's find I sub B, I sub C, and V sub EC. If beta F is 100, V sub EB on is 0.7, and V sub EC sat is 0.2. Because we're looking at biasing, let's assume we're in the active region and see whether the numbers work out or not. Between the emitter and the base, I'm going to put the V sub EB on of 0.7. Between the emitter and the collector, I'm going to put a current-controlled current source of beta FIB. It's the same model we had before, but everything is flipped. My battery's connected to 2 points, so let me take this part off and Thevenize it. Open circuit voltage is 22K over 10K plus 22K times 15, that's 10.31. Set this equal to 0, you see 22K in parallel with 10K. We're going to replace our 2 resistors and a battery with just 1 battery and 1 resistor, Thevenin equivalent circuit. Our model is still again between the emitter and the base and the emitter and the collector. Here I've got a current coming in here, but what's leaving is I sub B and 100 I sub B, so this is 101 I sub B. Go around this loop, we get 1 equation and 1 unknown. If you were to go around the loop this way, pick up another unknown, you'd have 2 unknowns, you'd have the voltage across here. We'll do this one first and we'll use this one second. 15 volts is equal to 101 I sub B times 1K plus 0.7 plus IB times 6.875K plus 10.31 volts. And that's this equation right over here. Solve for I sub B is 15 minus 0.7 minus 10.31 divided by 6.875K and 101 times 1K. That's 37 microamps. Multiply that by 100, it gets 3.7 milliamps for the collector current. And then the voltage is 15 volts minus the drop across here, minus the drop across here, because these 3 added together gives me 15. Subtracting the top resistor and then the bottom resistors, voltages, I get 7.56 volts. I sub B is greater than or equal to 0, and V sub EC is greater than V sub EC sat. So we are in the active region. The procedure is very similar to what we did for the NPN transistor, but our models are just flipped. We could do the same design procedure by just stating it. I'm going to pick the current in this resistor to be at least 10 or 20 times bigger than the biggest possible I sub B, and they'll give me a voltage here that's equal to R2 over R1 plus R2 times VCC. And by doing that, I have a voltage here that's independent of beta F. We'll drop a third of the power supply across here, a third across here, and a third across here. And that'll make the voltage across here roughly equal to about a third of the power supply if VCC divided by 3 is much greater than V sub E beyond. And this is biasing the BJT.